I'm going to show you how to calculate the required ventilation for each zone and the required outdoor air intake for your system using ASHRAE 62.1 methodology. This is fundamental to commercial HVAC design, and if you have young engineers on your team, you'll probably want to share this with them. Here we go. Step 1. You're going to determine the required outdoor air rates for your space and calculate VBZ. VBZ is the ventilation CFM to the breathing zone of your space. Calling it the breathing zone is just another way of saying the ventilation CFM that actually gets to our occupants. You may introduce air to a space, and a portion of it may not actually get to the occupants. So what we're looking for here is how much fresh air do these occupants actually need to breathe. This right here is the equation used to calculate VBZ per ASHRAE 62.1. Let's break down these variables. So RP is your people rate for outdoor air, and P is the number of people. RA is your area rate for outdoor air, and A is the floor area of your space. RP and RA can be found in ASHRAE table 6.2.2.1. It looks like this. So to find those rates, you would find the space type that you're calculating for, say an office space. And this is my people rate, this is my area rate. So let's get those down. For an office, my people rate is 5 CFM per person, and my area rate is 0.06 CFM per square. In this office that I've drawn here, we have 2 people in 300 square feet. That gives us a VBZ of 28 CFM. We're on our way. Step 2, we need to calculate the OZ. This is the design ventilation CFM to this zone. We talked about the breathing zone. We need 28 CFM of outdoor air for these occupants. So now we're asking how much CFM total do we have to bring into the zone, accounting for any drop off, so that we get 28 CFM of air to these occupants. To calculate the design ventilation to the zone, this is the equation. It's the ventilation to the breathing zone, which we just calculated, divided by the air distribution effectiveness. The air distribution effectiveness depends on your distribution system. Overhead supply is different than underfloor supply, and cold air is different than warm air in terms of how it's going to disperse into the space. Table 6.2.2.2 in ASHRAE 62.1 gives you a list of EZ based on your distribution type. This is what that table looks like. So for ceiling supply of cool air, we have 1, perfect distribution, essentially. With warm air at a 15-degree or greater delta to the space, it's going to be 0.8. So look at what conditions you're designing for and find your EZ in this table. In my scenario, I will be providing warm air with a 20-degree delta T to the space, and so I'm going to select an EZ of 0.8. And with that, that makes my design ventilation 35 CFM. Now, if you have direct to zone ventilation, you're pretty much done. That's all you need to do. You would do steps 1 and 2 for every zone under your system. You would find that VOZ, 35, 40, 25. You would sum them up, and that would be your outdoor air intake. However, this is for direct to zone ventilation, meaning all of your outdoor air is coming through and going directly to the zones that it's ventilating. A classic example is you have a dedicated outdoor air unit serving indoor fan coils, maybe a VRF system. The point is, the outdoor air can be delivered directly to each zone precisely. Each zone can get exactly as much outdoor air as is calculated per steps 1 and 2. However, if you have central ventilation, where the outdoor air is mixed with the return air before it gets distributed to the zones, then you've got some more work to do. In a system like this, you do not have that precise control over how much CFM of outdoor air goes to each zone. It all mixes together and then gets distributed as a mixture to each zone. So we've got to play with some percentages. From here, we need to calculate ratios so that we know what ratio to use when we're bringing in our outdoor air. And ultimately, we're trying to figure out what is the total outdoor air intake right here. With a central mixed ventilation system, step 3, we need to find the ZP, which is primary outside air fraction. To find ZP, we need to know what the total design supply airflow is to this office space. So you've done your load calculations, you know your space sensible calcs, you know your delta T. You can find the required CFM to handle the cooling load in this space. Let's say that is 250 CFM. To calculate your outdoor air fraction, ZP, it is your VOZ, the ventilation to the zone, divided by your total supply air, your VPZ, which is the supply air. With a design supply of 250 CFM to the zone, That makes our outdoor air fraction 35 divided by 250 equals 0.14. But wait, that's not good enough. This is not the correct outdoor air fraction. We need to find the adjusted outdoor air fraction, which is essentially the outdoor air fraction at the minimum operation of your VAV. If one of your zones is operating at the minimum airflow, you still need to provide the correct amount of outdoor air. So we need to find your outdoor air fraction for a reduced CFM, the minimum operation. Typically, that's about 30% of your total design supply CFM. So for that, we just need to adjust the supply. 30% of 250 CFM is 75 CFM, which means our adjusted outdoor air fraction is 0.47. Step 5, we now need to do steps 1 through 4 for every zone. We need to find the adjusted outdoor air fraction for all of these zones. So this one is 0.47. Let's say this one is 0.3, and this one is 0. Once you've done this for every zone in your system, you can find your maximum. I'm going to stick with 0.47 in this example. And I know what you're thinking. Okay, great. So the total air intake is just our max outdoor air ratio times our total supply for this system, right? Nope. There's a bit more work to do. We're actually going to use that maximum outdoor air ratio to find our system ventilation efficiency. So step 6 is find EV. This is an ASHRAE table lookup. We're going to use table 6.2.5.1 to find our EV based on our ZP adjusted. Here's what that looks like. Given a range of ZP, it gives you the correct system ventilation efficiency. So we're at 0.47, just over 0.45. So we're going to have to go with an EV of 0.6. An EV of 0.6, just put a pin in that. We're going to use that in step 8. But first, we need to calculate VOU. This is step 7. Calculate the uncorrected outdoor air intake. So this is for the whole system. The equation for VOU is D times the sum of your people rate times people plus the sum of your area rate times area. So you may remember from step 1, we already saw this equation. Now we're calculating it for the entire system. And when you're looking at the whole system, you can benefit from people diversity. So what is people or occupant diversity? It's the actual total number of people divided by the sum of the zones total. So when you have a large building, each zone is designed for a certain number of people, but when you apply diversity, you're assuming that not all zones are fully occupied at the same time. For an office building, people may be in a conference room, that's one zone, but if they're in the conference room, they're not in their offices. So there's a little bit of diversity in the total number of occupants. And this is actually a way for us to reduce the amount of total outdoor air we need to intake. If you're being extremely conservative with this calculation, your occupant diversity can be 1, in which case your uncorrected outdoor air intake for your system can be equal to the sum of your zone ventilation CFMs from step 1 in this video. To continue this demonstration, let's assume I ran this calculation and my uncorrected outdoor air intake for my system came out to 1,750 CFM. Now, finally, step 8, we calculate the outdoor air intake, the corrected ventilation air that you need to bring in to your system. Our VOU was 1,750, and from step 6, our ventilation efficiency for the system was 0.6. That means the outdoor air intake required for our system is 2,917 CFM. That's this right here, the outdoor air intake into a centrally mixed system, 2,917 CFM.